example of a machine learning algorithm. Here, I wanted to use linear regression to talk about and explain how a machine learning algorithm actually works in practice. So linear regression is actually a recursive model that finds a best fit line over the data points by minimizing the difference between the data points and the line. You may be familiar with this from statistics class, but if you're not, hopefully this explanation would be sufficient. So imagine you have some data here. Let's say that this is price over here, price of a stock or price of something. This is time on the x axis. Let's put some marks here just to kind of facilitate 0. So this is like 1, 2, 3, 4, 5, 6, going up 7, 8, 9, 10. Oh, look at that. 1. Oh, this is 1. Okay, so these are the prices. This is the time. We have existing data points. What linear regression does is it tries to find the line that minimizes the difference, the cumulative difference between each data point itself, and the line. Now these are kind of, there's a lot of points here. There's a long rectangle, so it's not one data point, but you can imagine, let's say, the central point in each of these. So the linear regression tries to find the line that minimizes. So if we were to test a line like this, the algorithm would test actually that and see, well, the difference of the points to this line, all of the difference of this point to this line I just drew here are much higher than the difference of all the points to this line. So the linear regression finds the line that minimizes the difference between the existing data points and the line itself. And we can then, why is this useful? Well, we can then use this line to understand the trend and the pattern. So if we have a particular time in mind, we can know the price. Now, of course, the line itself, so for example, if you give me the time December 27, the price is going to be here around 5 because the price is going to be on the line. Now, that's not the actual price that existed, but the whole idea is that we find a trend and a pattern. So the linear regression ultimately produces a linear equation, such as the one represented here, which you may be familiar with. So Y is the outcome of interest. So in our case, this is going to be price. A is the y-axis intercept. So this is kind of like the baseline where we're starting. B is the coefficient or effect or size coefficient. Oh my God, sorry, it's coefficient. And X is the data point itself, the data value. And in this case, it's going to be some kind of time. So the linear regression essentially produces a linear equation. And once again, the usefulness is that if you give me a data point, I'll give you plug it in to the equation, and then you find a relevant price. Now, for the existing data points, maybe it's not so useful. But the idea is that if you develop this line, this is of course the slope of the line as well. So if you give me, so this is December 27, so maybe if you say January, we can kind of imagine that the line keeps going here. So the price in January is going to be, if you put January 30th, the price may be like 12 or something, right? Because we had like 1 and 5 and 10. So you just continue along. So this is how predictive analytics works. What's also useful about the regression is that we do not need to only work with one single feature or one single factor. We can have multiple of them. And so in the case of the stock price, we may want to add other factors as well. So, time is one factor, but also other characteristics may be factors. So inflation may be a factor. Earning per share may be a factor. Consumer sentiment may be a factor. So suppose we can't really, it's hard to draw and depict, visualize all of these dimensions because just the way paper and two-dimensional interface work. But we can calculate it algebraically. So we can create a linear regression line that actually includes multiple features. And what the linear regression does, it finds the coefficient B, and which identify the relevance or the impact of each of these variables or factors on the price, on your outcome of interest. So some of these may be positive. So for example, the price, the time, as time goes forward, price goes up usually, or he finds this from the existing data. Remember, we have to train on the existing data. Inflation, though, is inverse. So B here would be negative because the higher the inflation, the lower the price, potentially, maybe not. The higher the earnings per share, maybe this would be a positive relationship. The higher this value, the higher the price. And the linear regression can find that. You can identify, we only see one here, one or two dimensions rather, but we can actually implement multiple dimensions, and the linear regression can find the coefficient of the impact of each of these factors on the outcome of interest. So here we have an example. Maybe we can bring up that example we discussed earlier. We can identify the variables that can predict how well others will mention or report on your company on the social media sites or websites. Now, this may be a little tricky, but I wanted to think about it and identify what the variables or what the features are going to be. Now, all the B's, this is what the algorithm itself would find. But we need to have the features that are relevant for us to feed and train the model. So you can pause here and think a little bit about what the relevant features or variables are that can be used to predict how well others will mention or report on the company. Now I'm going to try a stab at this and think about it. Well, first of all, how are you measuring this outcome of interest? What does the data look like? How do you operationalize it? Well, you have to operationalize it somehow. So maybe it can be something like positive comments. So the number of positive comments or positive associations of the company or company product so the positive association of the company or company product with some positive sentiment. Some of the other features that can predict, it can be noticed that this here in a regression, this has to be numeric. Okay, it can be actually binary, 0 or 1. We would have a different kind of regression, but it's generally numeric. Now, what are the features that can predict the positive comments that are going to appear on the media? Well, maybe the media type, right? That's one. So these can be categorical here. Media type, maybe on social media, people don't talk well about your company, but on the regular media, they do. So media type may be a factor. How about the existing stock price? Existing stock price. So notice how the stock price before was a variable, an outcome variable of interest. Now it's become an explanatory factor. Media type, existing stock price of the company. If the stock is higher, maybe more people will mention you notice we only have one. So we're just talking about number of positive comments. Higher the stock price, the higher the positive comments. Media type is categorical. So it's kind of hard to add here. We have to do some translation. So I won't add positive or negative, but we can get the idea of the overview. What else? So, maybe charitable actions. So if your company has done charitable actions, will the media pick up on it and provide greater positive comments? So, this is number of charitable actions that the company has taken. So hopefully you kind of got a sense of how this works and you can apply this to your own context. Of course, there are issues with machine learning. Just because the trend before was to go up, and just because the more time passed forward, the higher the price, it doesn't mean it's going to continue that way, right? Things can start going down, and the business of prediction is a very unreliable one. And of course, there are many technical and otherwise issues with machine learning. There's often difficulty in interpretation of the models. We understand that correlation is not causation, but what the models usually find is just causations, association between certain variables and other. There's often a multiplicity of factors adopted, so we're kind of just playing around with 1 or 2 or 3 here, but often there are hundreds or thousands of attributes, once again, because of the data that are being accumulated and available. So people are just feeding in kind of any, not just any data, but feeding in whatever they can see to, whatever they can find to be predictive of something else. And that makes it very difficult to interpret. So it's they call this the black box phenomenon. Data quality, so there's issues with sampling bias. So depending where you're getting your data from, you may have biased data, and that can give you information that may be predictive in the short term, but not in the long term, or not applicable across contexts, right? So if you're selling some goods in California and you learn from data from people in California, if you apply that to Tennessee, you may not get the same results. Inherent difficulty of predictability of the future. So we live in a complex world. It's constantly changing. There are things like, black swan phenomenon, or things that people are just not expecting that just happen, and that can impact the models. And also, of course, on a more societal level, machine learning algorithms, and this is kind of where the image here is alluding to, they can reinforce existing social biases. So because we're developing the systems to integrate the existing relationships that have already existed in the past, then our models and the way our technologies and analyses work is to perpetuating existing negative patterns by building on them. And this is really well actually discussed about in this book here, but also by a number of other individuals talking about machine learning and artificial intelligence nowadays. I hope this was useful to you, and I'll see you next time.